Okay, we're looking at a Brayton cycle with a regenerator on it. So it enters at 14 and 77 degrees Fahrenheit, which is 537 Rankine. It's compressed to 60 pounds, goes through the regenerator, comes out 1120 Rankine, goes into the turbine at 1700. Okay, both the turbine and the compressor have an isentropic efficiency of 84%. So really I have, and again I'm looking for H values to set my state. So I have H1, Hx, H3. I can look all of those up. Then what I need to do is, here's my compressor. It has an 84% isentropic efficiency. So I'm going to look up PR1 and use it to calculate PR2S. From that, I'm going to get H2S. And then from the 84% efficiency, I'm going to get H2. Okay, this is the regenerator. 3 to 4 is my turbine. So the same idea. It has an 84% efficiency. So I'm going to use PR3, which I can look up. Use it to find PR4S. Again, it's going to be the same pressure ratio going back, from the turbine back to the atmospheric pressure that's ultimately going to get pumped out. So use that pressure ratio. That'll give me H4S, and then again using the isentropic efficiency I can look up H4. And in fact, I don't really need HY to figure out what I'm looking for here, which is the thermal efficiency and the regenerator effectiveness. So I'm just going to ignore looking up state Y here. So there we go. So let's go ahead and we'll start with 1, X, and 3 because I've got those values. So I'll start with the 537. Okay, this is air, so 537. I've got H of 128.34 and a PR of 1.3593. Okay, then state 3, I go to 1120. So at 1120, H is 271.03 and PR is 18.6. I'm not sure if I needed that PR. Nope, I sure didn't. State 3 is what I need a PR for, and that's 1700. So again, H is 422.59, and then my PR is 90.95 right here. Okay, so I've got all of those values. Let me go ahead and jot those guys down. So then H1 is 128.34. The relative pressure is 1.3593. Okay. State X is given to be, there it is, 271.03. H3 is 422.59. PR3 is 90.95. So I looked up the 395. Looked up the 3 states that I have. Okay, so now I'm going to do the compressor and the turbine using the efficiency. So first things first, I'm going to find PR2S, the isentropic case, the best case, using my pressure ratio that I have here, right? I know my pressures, I know PR1. From that, I can calculate PR2S to be 5.625. Okay, now that I have PR2S, I can look up HS. Okay, so let's go ahead and do that. So 5.625, I go over here, and 5.625 will be in this range right here. Gives me an H of approximately 192.76. Now this is the ideal enthalpy if it was isentropic, 192.76. However, this is not ideal. Okay, so I'm going to use my isentropic compressor efficiency, which is the ideal over the actual, right? Because I'm actually going to have to put in more than ideally I would have to. So I know H2S, I know H1, I know 84%. From this, I can calculate H2, and H2 then becomes 205.03. So that sets state 2. So I'm going to do the exact same thing with the turbine, right? Again, PR4S over PR3 equals P4 over P3. Of course, that is the same pressure ratio, just flipped as what I had before, right? P4 and P1 are the same because they are being pulled in from the atmosphere and getting dumped to the atmosphere. And then P3 and P2 are going through the same set of heat exchangers, so that would be like that. So again, I know P1 and P2. I know PR3 from this. I can calculate PR4S to be 21.98. Okay, so this is the ideal relative pressure if it was isentropic, which it's not, but I have to go look that up. So H4S at just about 22, just shy of 22 for a relative pressure. So I'm right in this range. Okay, so the ideal enthalpy coming out of the turbine would be 284.01. Okay, so 284.01. Okay. Now that I have that, I'm going to use my isentropic turbine efficiency to calculate what H4 actually is. So that's going to be H4 minus H3 all over H4S minus H3. So again, actual over ideal equals 84%. Again, I know my turbine efficiency. I know H4S. I know H3. The only thing I don't know is H4. I can calculate that to be 306.18. And again, I do not need state Y to calculate what it's asking, so I'm going to go ahead and skip that step. Now I have all of my states that I'm looking for. So to find the thermal efficiency of the cycle, it's just the work of the cycle, over Q in. So that's going to be the turbine, which is H3 minus H4, minus the compressor, H2 minus H1, divided by Q in, which remember is just this, right? This is the preheat, this is the regenerator, this is the combustor, so it's H3 minus HX. And this is what's smaller than what it would be if I didn't have the regenerator. Okay, plugging in all of those H values there, I can find that the thermal efficiency is 26.2%. So pretty low. Okay, but again, it's just work of the turbine minus work of the compressor over Q in, which is smaller than it would have been if I had gone, directly from 2 to 3 without that regenerating preheat. Now, by definition, the regenerator effectiveness is HX minus H2 divided by H4 minus H2. Because again, remember the best thing that the regenerator could do is make X and 4 the same. Okay, which they're not. Okay, and they shouldn't be. They can't. Just physically, they can't do that. Okay, but that would be the best case. There's certainly no way it could go, get X higher than what 4 was. Okay, so that's the best case. This is what's actually going on. We can calculate that regenerative effectiveness as 65.2. So as with most problems we do, you go through, you set your states here. It's with H. Given 3 of them, I have to do relative pressures and isentropic efficiency to set state 2 and 4. And once you get that, then it's just to find the efficiency. It's turbine minus compressor over Q in. And regenerator effectiveness is what I'm actually getting for enthalpy change over what the ideal would be using H4 minus H2.